ladies and gentlemen, 10 o'clock. Welcome into the online world, and welcome back to your favorite class. Yes. Hope you like the meme today submitted by one of the students in my composites class. It's like a Godzilla breathing fire. Roar! Okay. I hope we enjoy that one. Okay, a couple of announcements. Homework 7 was due like 1 minute ago. So hopefully you got that in. Joe, I'm muting you. Okay, so hopefully we got that in. I've released the ungraded homework number 8, which is on fatigue. It's kind of the stuff that we're covering right now. The full solution for that has also been released, so I'd say maybe wait a couple lectures before you give that a go, but there will be a fatigue problem on the final exam. There will not be a fatigue problem on the exam next week, which brings me to your second exam for the class is going to be in the lab period next week, okay? So I've released some practice problems for you to sort of take a look at. There's like buckling and pressure vessels and non-circular thin-walled torsion and all that sort of good stuff, okay? So take a look at those practice problems. I think there's like 15 or so of those that you can give a go. We'll have a review session on Monday night at 7 p.m. if you'd like to come. That's optional. You don't have to come if you don't like. But there will be a review session next Monday night. We're going to go over some of the practice problems from that exam. And obviously your exam next week will be in the lab period. It'll be much like the last exam. 100 minutes to do it, 10 minutes to turn it in, open everything. All right, so that's what's happening currently. Your final exam, I think, is Wednesday, right? 11 to 1. Can anyone verify that? Anyone know that off the top of their head? I think for the class, this class, your final exam is the Wednesday, which I think is the 18th. Is that right? 11 to 1. Yeah, okay. Thank you. So there you go for your final exam. All right. Any questions? Okay. Then let us get back to where we were. No plasticity. No, just kidding. Different class. All right. So we were talking about fatigue and endurance curves. But before I get into that, I want to talk about the lab you just turned in very quickly. So quickly, an aside. Okay. And this is from the non-circular torsion lab. All right. So your non-circular torsion lab, you should have seen that when you're doing the calculations for this sort of like rectangular cross section, we know from the non-circular torsion portion of the class that shear stresses will be highest in the cross section of bar at like these general locations. All right. So in these particular spots, you'll have like the maximum shear stress. You should have seen that like the error for the modulus calculation on this side of the bar that you had like some high error. I think it was like 28% was approximately the right number. All right. On this side of the bar, your error was lower. It was like 3% or something like that. Okay, approximately. When you're calculating the moduli for your lab. Now, we know from our lecture of non-circular members and torsion that we're going to have like the max shear stress sort of on this like center of like the long sides, the center of these like sides of the bar. We also know that at like the edges here, these corners, your shear stress is equal to 0. All right, for all these 4 corners. Okay, so the question is, why was the error so high on the short side, but the error was so low on the long side? I had a lot of very interesting responses, most of them incorrect. Okay, so let me explain why that would be. All right, so if we think about what the distribution of the shear stress might look like on these sides of the bar, it's going to look something like this, where if you have some maximum value that's like up here, it's going to sort of taper off to the edge. It looks sort of something like this. Okay, that's going to be what your distribution generally looks like. Same thing on the long side of the bar. All right, it's kind of coming up like this, and that's not a very good drawing. That's a little bit more appropriate. All right, where it looks something like that. This is your distribution of the shear on either side of the bar as you're looking at the bar. The question was, why is the error so high on this top side of the bar? And many people came up with ideas, but most of the ideas, sus, as they say in what's the game? What is it? Among Us. Yeah, okay. Very sus. All right, it's like they're stealing my word. Very sus. All right, suspicious. Okay, so remember in our lab we had strain gauges like on the top and the bottom of the bar. I want to bring in a picture here that shows what the strain gauges actually looked like on this particular piece. So here's a slide from the lab where we have the various strain gauges on the piece. At the top of the bar, we have the strain gauge here, which is the shear T we sort of spent a lot of time talking about. On the side of the bar, we have the strain gauge rosette. All right. Not necessarily important that it's two different types of gauge, but I want you to notice in this particular picture how much space this strain gauge rosette here actually like occupies on the short side of the bar. It's almost like to the far edge over here. Same thing on this side. This gauge is like almost to the far edge over here. All right. So when I think about like this particular picture, let's see if I can bring this in here. Is it going to blow everything up? No, it's not blowing everything up. All right. What I'm saying here is that this gauge here is like occupying so much real estate on this particular side of the bar. Okay. So what do I mean by that? All right. Well, what I mean is I'm basically measuring the shear strain over like this whole region of the bar. Right. Same thing, I'm measuring like the shear strain over this whole region of the bar, right? On the longer side, I have a similar idea, except it's much less of the total length of the cross section, right? So here's the general idea. When I'm measuring with this shear T rosette on the top side of the bar, I'm basically taking like the average of this portion of the distribution and the average of this portion of the distribution, and that's basically the shear stress that I'm reading, okay? We see here that because the gauges have like such a wide width that actually the real value of the shear strain kind of like on the far edge of that gauge is relatively small. All right, maybe it's only like 50% of what the maximum value is. Same thing on this side over here. It's maybe only 50% of the maximum value. Okay, so I'm trying to measure the shear at like the center of this particular bar, or I've assumed that I know what the shear stress is at the center of the bar here with this calculation tau max. But because of like the width of this strain gauge, I'm actually measuring significantly less strain at that point than I would expect. Okay. So generally, I might get some portion of my strain reading that is significantly less than what is actually happening at the center. That's different from the long side of the bar where, yeah, I'm measuring some amount, but generally that amount is equal to the maximum, right? That's just because these like shear T's just take up so much width on the top side of the bar. And so the explanation here for why the error is so high at the top has something to do with the measurement that we're taking of the shear strain on the top side of the bar. The distribution of the strain on the top side of the bar is such that because of this displacement of the gauge off the center, we have a significant error because of its displacement off of the center of the top of the bar. All right? It's amplified on the top side of the bar as opposed to the side of the bar, the long side of the bar, because the amount that the gauge is displaced off of the center, percentage-wise, on the long side of the bar is much less. Okay? So hopefully we sort of like see and understand that. That was the correct explanation. Some people were like dancing around that idea, but you know, you had to say something like the distance the gauge is displaced from the center of the side is significantly more on the top than it is on the side. That was more or less the right explanation. Okay, rant over. Let's get back to fatigue. Are you fatigued by my explanation? Okay. What's that? He's enlightened. Oh, that's good. I'm glad he's enlightened and he's not fatigued. But let's get back to fatigue, and I hope you're not fatigued by it. What? Okay. The last time we were talking about endurance curves and modifications to the endurance limit. So last time we were talking about endurance curves, which more or less is plotting on the y-axis This is endurance curve. The stress amplitude that we can handle. Reminder, this is sort of like the time, and here's our sort of stress distribution that we're sort of like assuming. And just a reminder that your stress amplitude is this value. So your stress amplitude, we're assuming sort of like the cyclic distribution. We're varying the stress amplitude and saying how many numbers of cycles to failure do we expect, okay? We said that if we're failing with 0 cycles, we're at the ultimate tensile strength, SUT. Some portion below that, we have the yield stress, which we're calling in fatigue here, SY. And then there's some low value of the stress amplitude, which we're calling SE, which is the endurance limit. The idea here is that as we lower the amount of stress that we're applying to our piece, we have more and more cycles to failure. And it looks something more or less like this in general. All right. Or here, this is called our endurance limit. This is usually around 1 million cycles or 10 million cycles. All right. So the idea here is this endurance limit, SE, is the stress that you could theoretically apply to the piece infinitely many times and it would never fail, right? So if we're designing a piece and we want it to sort of, quote unquote, never fail in fatigue, this would sort of be our design criteria. We would want to design towards this endurance limit, right? If we were expecting unlimited or infinite cycles applied to our piece, all right? Now, we said that this particular curve is made for a variety of materials, and it looks different for each material. Okay? And not only is it different for each material, there are also other things that can affect how this curve takes shape, and other factors, such as surface roughness, surface area to volume ratio, applied load. Okay, could be axial fatigue, could be bending fatigue, could be torsional fatigue, right? So the applied load matters, surface roughness matters, surface area to volume ratio matters, maybe the temperature matters. Okay, all these things like can affect what this curve looks like. And so, yeah, maybe this is like your curve for a pristine specimen. But what if the temperature is 100 degrees Celsius less? All right, well, then maybe your curve looks something like this. Who knows? Okay, and so now if you're operating in a lower temperature, you have some new endurance limit, which is some SE modified. Okay, some modified endurance limit that you now want to protect against. So what we want to do over the next lecture or so is say, if we're operating at a different temperature, if we're operating with a different surface roughness, if we have a different size specimen, if we have a different loading type, how does that affect our endurance limit? So what we want to do over the next lecture is, how does this value vary with all of these parameters down here I just wrote? Surface roughness, surface area to volume ratio, applied load, and temperature. That's what we're kind of going to talk about in this lecture. All right. So we'll introduce a new variable here. And that new variable is SE prime. SE prime is the pristine endurance limit. What do I mean by that is the value that you get from the RR more high-speed test. Okay, so this is a very standardized test that must be done to sort of establish what is this pristine baseline. All the samples that have this pristine value coming off are the same size, they have the same surface roughness, they have the same character of applied load. Everything about the pristine endurance limit is very controlled. Okay? Then we modify this pristine limit for our certain situation based on temperature, size, applied load, etc., to get what our actual endurance limit is. Okay? And we do that using endurance limit modification factors. Okay? The basic equation that you'll see for endurance limit modification factors is something like the following. SE, which is your actual endurance limit given your particular situation, is given by something like C size times C surface times C load times C temp times whatever variables that might otherwise affect your situation multiplied by the pristine endurance limit. Okay, so here this is your actual endurance limit. These are your modifying factors. And this is your pristine endurance limit. Okay. A reminder, we can get this pristine endurance limit from sort of the charts that we talked about last time. Okay, so just as a reminder, we already sort of looked at the tables that kind of looked like this. Okay. Notice here that we're incorporating the prime here. These are pristine endurance limits for these particular materials. So I just want to be very clear about that. So when you're looking at your equation sheet and looking at, calculating what is the endurance limit for your current situation, you want to start with the pristine endurance limit, which is gotten from this particular chart. Okay. All right. So let's actually talk about what these endurance modification factors are. All right. All of these modifying factors, they all come from experiment. They all just derive from empirical methods. Okay. The only ones we're going to talk about in this class we're only going to talk about surface condition modification. So CSURF, which is surface condition. Okay, the rougher the surface is, the lower the endurance limit will be, just because you have more flaws from which to propagate cracks. Okay. We're going to talk about load modification. So this is C load. So this is load modification. And this basically is a factor that tells you how things change, whether you're doing like a tensile loading, whether you're doing a bending loading, or whether you're doing a torsional loading. Last one that we're going to talk about not temperature, that one's really quite complicated, is the size modification. And this really has to do with the surface area to volume ratio. All right. The more surface area you have to volume ratio, the higher your likelihood for flaws to affect the ultimate performance. Right? If you have a very high volume and a very low surface, that means that most of the load is going to be carried by that internal volume, and your proclivity to have a lot of flaws that propagate cracks on the surface is very low. But the more and more surface area that you have, the more and more possibility there is for a flaw to exist, which limits your ultimate performance. That's the idea. All right. So there are analytical models for each of these, and we're going to sort of tackle them one by one. The first one that we want to do is we're going to talk about surface modification. All right. More flaws leads to earlier failure. Pretty simple. The rougher the surface, the more flaws. Okay. So basically the idea here is that we want a model that captures a basic idea of how much roughness affects the ultimate performance. And the general formula here is this. That this surface modification, C surf, I think in the notes I use K. Your book uses the variable K instead of C. Your equation sheet uses C, so I'm going to stick with C here. The surface modification, here's a constant variable A times SUT, which is the ultimate tensile strength, to the B. This is your general formula for surface modification. Okay, SUT, this is your ultimate tensile strength. Okay, A and B are constants that depend on the surface roughness. I'll say surface finish. Okay, and there are many tables that exist that tell you if I have a milled surface, what's my value of A and B. If I have a hot rolled surface, what's my value of A and B. If I have a cast surface, what's my value of A and B. I've included the one from your equation sheet and also the one from your book in the notes, and I'm just going to post that here. But there are many other values aside from this that exist. And again, this is strictly from experiment. And it looks something like this. Just move this up. Oh God. It's a disaster. Okay, whatever. Stupid technology. So here are your values. This is from experiment, and this is tables in your notes. All right. So this factor A, I'm Canadian. This factor A, it depends on whether you're working in like English units or standard units. So be careful with that. But the exponent B doesn't matter whether you're in English or standard units. Okay. And various surface finishes give you certain modifications. Last thing I'll say is if surface is pristine, then the surface modification value is 1, obviously. Your endurance limit will be equal to the pristine endurance limit if your surface of your material is pristine. Otherwise, get thee to this chart. All right, let's look at an example. Let's say we have steel alloy, tensile strength 520 MPa. All right, and let's say it has a machine surface. Okay. We'll find what is our endurance limit. And we're going to assume that it otherwise has the geometry of the RR more specimen and is in bending. All right. So first what we want to do is we want to find the pristine endurance limit for this piece. All right. So first, we want the pristine endurance limit, and that comes from the tables. So as a reminder, let's go back to our tables. This is the table. It's in your particular equation sheet. Here we're told that this particular steel has an ultimate tensile strength of 520 MPa. So obviously we're not greater than 1460. So we're less than 1460 MPa. So our general equation that we want to use to figure out the pristine endurance limit is 0.504 times the ultimate tensile strength. So here then, SE prime is 0.504 times the ultimate tensile strength times 520 MPa, or we'll have the pristine endurance limit here, which is 262 MPa. Okay, this is our pristine value. We have not yet modified for surface finish. This would be what the endurance limit would be if the surface was perfectly pristine. Okay, now I need surface modification. So the general formula I'm going to use here is that my modified endurance limit is surface modification value times the pristine value. Right? Where this C surf is equal to A SUT to the B. Right? For machine finish, we can go to our table to get the values of A and B. Give you a second to catch up. Keep in mind that we're working in standard units here. It's going to be important for our, when we go to the table, for our value of the constant A. Value of the constant A. All right. So a machine or a cold drawn surface, we take a value of A if we're in metric of 4.51, and our exponent B is negative 0.265. So for machine finish, your value of A is 4.51 MPa, and your value of B, negative 0.265. Okay, it's my exponent. Okay, so then C surf is equal to 4.51 times my ultimate tensile strength, I know here is 520 MPa, to the B, which is negative 0.265. Yeah, there's a problem with this chart. This variable A should actually be 1 on MPa. It's actually 1 on MPa to the b, which is a little complicated, but just roll with it. All right, so we calculate all this out, and you're going to find that your surface modification is 0.860. All right. So because of this particular roughness that I have, I'm going to reduce the pristine endurance limit by 86% to get my actual endurance limit. That's just because the increased amount of flaws on my surface leads to a higher proclivity for failure before the predicted endurance limit. My surface modification times my pristine value, which was 262. And so your actual endurance limit for this particular piece is 225 MPa. So for this particular piece, if I wanted to design against infinite cycles to failure, the stress value or the stress amplitude that I would want it to be less than 225 MPa. Anything more than that, you would ultimately fail at some high level of cycles depending on, the amplitude. All right, that's the general idea. Okay, so that's your surface modification. Next modification we want to talk about. Size correction. All right. The RR Moore test assumes a circular specimen of a certain size, but you're not limited to circular specimens. I mean, in real world, you use rectangular, triangular, whatever. Okay, you got a lot of different cross sections that you could use, and also you're not limited to whatever the size is of the RR Moore test. Okay, you could have a circular round of whatever diameter. Okay, it doesn't really matter. Okay, but the point is, as you change your size, you will change the surface area to volume ratio. And you need to be able to account for that because the more surface area you have, the more flaws you have. Okay? So, size correction factor. Size and shape. Change surface area to volume ratio. More surface area leads to more flaws, or more truthfully, more flaw density per volume. All right? So that should lower your endurance limit. All right. So the size correction looks it's a little strange, but a bit complicated. But let's talk about it. Generally, you're going to use the variable C size. And the calculation of C size depends on the hydraulic diameter. And if in bending, whether you have rotating or non-rotating bending. Let me explain. We need to talk about rotating bending. Okay. In rotating bending, all points on the outside of a cross section will feel the maximum stress. The RR more test is an example of this. Okay? This example with this particular, bending specimen that we sort of talked about already. If you're on some axis here and you're rotating with some motor, and this thing is in 4-point bend, okay, so this thing is spinning around. All the points on the outside of this cross section will ultimately feel that stress amplitude. So at this particular snapshot in time, yes, the top is in compression and the bottom is in tension. But since the sample is rotating around, every single point on that red circle that I draw on that sample is going to, at some point, feel the maximum compression and feel the maximum tension. Okay? So that's what I mean. All points on outside of cross-section will feel the mass stress. That's because I'm sort of spinning this guy around, and it's in this 4-point bend configuration, so every single time that this rotates around, every point experiences the maximum compression and the maximum tension. That's different from non-rotating bending. Only 2 points feel max stress. In non-rotating bending, instead of spinning a sample around some axis, like this, and all points are going to feel that maximum stress, if you have non-rotating bending, basically what you're doing is taking your sample and doing this. Okay? No longer is every single point experiencing the maximum stress. It's only the points on like the top and the bottom of this cross section that are going to feel the maximum stress. So you could think of this round specimen again if you want. This could happen in a round. Okay? Where no longer am I spinning this around a motor and holding it in 4-point bend, but instead I might be having some alternating positive and negative bending moment fluctuating in this way. Okay, sound effects required. Okay, in this particular situation, yes, you have this cross section occurring here, but you're only experiencing the maximum stress on this cross section at the top and at the bottom. So these 2 points here are the only 2 points that are experiencing the maximum compressive and tensile stresses. Okay, that's different from the rotating bending where all of these points are experiencing that maximum value. Okay, so in a non-rotating bending situation, you're only looking at these 2 points as possible failure points, basically the top and the bottom of the cross section. Okay, if those are very pristine for whatever reason, if they're perfectly polished, there's no flaws at that location, well, it's going to last for a pretty long time. But as you begin to test like all points on the outside of the cross section, the probability that you run into a flaw by testing more points on the outside of the section is much higher. So the probability of this failing before this is greater. Okay, so kind of equal moments applied, all things being considered equal, this will have lower endurance limit. And that's because you're more likely to expose a flaw when you have rotating bending? Okay. For instance, in this non-rotating bending over here, if I had a big flaw right there at that blue dot, that's my neutral axis of bending. All right, there's no stress that's happening at that point. So I'm never going to prematurely fail because of that flaw, because that flaw is never loaded, right? So that's how you got to like think about this. So we need some size modification that accounts for this sort of like unique behavior of rotating versus non-rotating applied loads. Okay, enough ado. Size correction, the following. This is in your notes. Here's what the equations actually look like. Some for standard units, some for metric. All right, obviously these standard. Sorry, English. This is standard. Okay. The idea here is you're going to calculate the size modification according to this equation if the diameter of your piece is between 0.11 and 2 inches. You'll use this equation if the diameter of your piece is between 2 and 10 inches. If it's outside of that, you need a new table. All right. Everything we do in this class will be somewhere in the range of this chart. Okay. So these are the equations that you have. Okay, well, what's D? All right. This D is actually DE, which is this value here. It's the effective diameter, or what's known as the hydraulic diameter. Okay. The effective diameter is something that you calculate for your cross section, and if your cross section is not circular, you have to come up with this effective diameter value. And it's calculated with this A95 variable, which is a statistical variable that we're going to talk about in a second. And it depends on the cross section that you have. Right. The A95 variable, there are tables that are given for that as well. Also in your equation sheet, looks like this. Here's how we calculate the A95 variable. And we have a situation of rotating and non-rotating bending, just as I sort of explained. So here, if you've got a circular cross-section with some certain diameter, if you're in rotating bending, take this calculation. Right. Notice that this would simplify, based on the equation up here, to just a little d. Right. If you have a square or rectangular cross-section, well, you can calculate your effective diameter as 0.05 base times height. Doesn't matter if you're rotating or not. Right. That A95 value gets fed up in here, and you can calculate your effective diameter, which then gets fed into your size correction factor. All right. Got some weird ones here for some like I-beams, here for some C-channel. We're loving C-channels after that last homework, right? Sus. Okay. All right, so you get the general idea. That's the method. When we come back on Monday, we'll do an example. So that's going to be it for today. I don't think I have time to get into an example. Happy Friday. Enjoy your weekend. Try not to get too caught up in election coverage. It's a little psychopathic at the moment. Happy weekend. See you on Monday.